In this video, we'll be talking about curves, and this curves video will be a little bit similar to the subsets video we talked about in the very first video, because we'll be going over a bunch of definitions that we'll need for the next video about line integrals. So let's get started. The first thing to look at is, what is a curve? A curve is what you might think. It's kind of like a path in the complex plane. So if I just draw some arbitrary curve here. Now there's a few things to be aware of a curve. This is not yet a curve because I have not designated a starting point and end point. If you just look at this, you don't know if it starts here, ends here, or what. So I'm going to denote the starting point by A, ending point by B, and then a little arrow somewhere to indicate the path of travel. So this is now a curve because it has a direction of travel, starting point and end point. And the notation we use to denote curves in complex analysis is often the Greek letter gamma of t. And this is a function. It's important to note also. A curve is a function. So this t, it must be a real variable. So t is an element of real numbers, and it must have a range. You must give it a range. That's part of the curve. So t is an element of, let's say, a to b. So that means that if you use gamma of a, that's the first point of your curve. And in that case, that's capital A. So to make it concrete, I'll write gamma of a equals capital A. And gamma of b, that's the last point on your curve. So that's going to be the uppercase B. So gamma of B equals uppercase B. And then now with this, all of this is information for your curve. So a curve, to recap, consists of starting point, end point. You have to have the range, and this t is a real variable. You can think of it as time if you'd like, but that might get a little bit confusing later on. It's more just like an indicator variable. It tells you, as you put different t's in, you travel along the curve. And then it has a path direction of travel. So now we're going to be defining some modifiers for curves, talking about making more restricted. So the first thing we'll talk about is a simple curve. So this doesn't really mean much to us, but let's try to give it some meaning. So in the most basic terms, a simple curve is a curve that does not intersect itself. So let me just draw one right here. This is a simple curve. So of course I have to give it A, B, direction of travel. In fact, both of these I've drawn up here. This and this are both simple curves because they don't intersect each other. In mathematical language, what that means is if I choose two different t's where the t cannot be the endpoint. So let me just write it here. Choose two t value and in big letters, not b. Or you can't choose this b. So you can't choose gamma of b equals b. That cannot be the point you choose. So choose any two other t values that are different. So different. And if you choose those, you should never be able to land on the same point on the curve. So let's see if that's true. So if I choose two different t values on this curve, remember, I cannot choose this endpoint. So I can choose a starting point. So let's say I choose the starting point, and now I choose a different t value and find where the curve is there. So let's say here. I should never get the same point on the curve. And indeed I do not, because if I start here and I move along the curve, it never loops around on itself. So now let's draw something to contrast. Let's draw, I'll draw in a different color. I'll draw an orange. So we'll start here. I'll draw A prime. And this curve will go like this and end at B prime. Okay, so now this statement is no longer true because let's say I choose this as my first t value, and as I'm going this way, I choose it here. Now the t value is increasing, and now I choose this t value here. But in fact, even if I chose those two different t values, I land on the same point on the curve. So this orange curve, not simple. These two purple curves are simple. So just the basic thing to keep in mind, they do not intersect themselves. Now a closed curve is more intuitive. It's basically a curve that is like a loop. So here is a closed curve. And of course, you need a starting point and end point. And the thing that defines a closed curve is this. Gamma of A equals gamma of B, which means that the starting point and end point must be the same. So this is both our starting point and end point. And our direction of travel is, let's say, this way. Now, important point to note, just because it looks like it's closed doesn't mean it's closed. For example, let me draw in blue what could happen. So let's say this is our starting point, just like before. And we go around the curve, around the curve, around the curve. And we don't stop, we go around a little bit more. Let's say this is our ending point. So even though this looks like a closed curve, the fact that we looped around it a little bit more means that gamma of A does not equal gamma of B, because gamma of A is here while gamma of B is here. So make sure that in your equation, when you plug A and B into the gamma, you get the same exact point on the curve. Okay, so now we're going to go over how to split a curve into components, and then we'll talk about a few more definitions. So remember, we have gamma of t, but since this is all taking place on the complex plane, gamma is a complex number, so we can split it into real and imaginary parts. So we can have x of t plus I y of t. So now x and y are both real, and y has an I in front of it, which means this is the real part of the curve, and this is the imaginary part of the curve. And now, since we can do this, we can also define the derivative of a curve. And we'll do that by doing gamma prime of t equals x prime of t plus I y prime of t. And that's going to be the derivative of the curve. So using this derivative, let me get this new paper. We're going to define smooth. So a smooth curve is one which has continuous derivative. So I'll write that. So continuous, CNTS, let's say, continuous derivative. Okay, so continuous derivative. And this, you can tell it by, again, this name is kind of, it tells the whole story. A smooth curve is one that looks smooth. So for example, here's a smooth curve. It's not closed, notice, doesn't have to be. So it goes from A to B. This is the direction of travel. This is smooth because as you go along it, the derivative is changing gradually, smoothly. There's no harsh jerks in the derivative anywhere. In contrast, here I'm going to draw on this complex plane something that will not be smooth. So if I draw like this, here's the starting point A, here's the ending point B, here's our direction of travel. This is not smooth, and the reason is because of this cusp right here. Because remember how we defined the derivative of a curve? It's going to be x prime of t plus I y prime of t. So in this case, while the x direction might be changing gradually, you might think, the y direction probably will not be, because we're going up on the y direction and then suddenly it goes down. So for the same reason in real numbers, why you don't have, why cusps causes discontinuity in the derivative, that's the same reason it happens here. But as I've written up here, this curve is piecewise smooth. And piecewise smooth means that you can break a curve into pieces and each piece will be smooth. And indeed you can do that here. So if you just cut it at the cusp right here using this orange line, we can have piece number 1 and piece number 2. And if you consider them individually, then they will be smooth because they're just nice smooth segments. So this is piecewise smooth. And it turns out that most things we'll run into will be piecewise smooth because you can almost always split things into little segments and have them each be smooth on their own. Okay, so now before we go on to the last part of the video, I just wanted to go over two things that might be misconceptions. You can have something that's closed and not simple. You can also have something that's simple and not closed. For example, this infinity looking sign, this is closed because you have the same starting and end point, but it's not simple because it has a self-intersection. Now this spiral is simple, but it's not closed. So it's obvious that it's not closed because the A is here and the B is here. And it's simple because it has no self-intersections. It always just, it kind of goes inside without touching itself ever. So that's something to keep in mind. Now this is the most important part of this video. It's about parameterization. And if you haven't come across this term before in calculus or want a refresher, parameterization is just finding the equation for some curve or line segment that we have here. So in the previous part of the video, we've been taking gamma just for granted. Now we have to form our own gamma. We have to just look at a curve on the plane and find an equation for it. So although that can seem daunting, and often it is, we will be able to do it if we have certain tools in our belt and know what to do. So first, let's do it for something simple, like a line segment. So we want to parameterize the line segment from 1 plus I, our starting point, going across to 3 plus 2i, our ending point. So it turns out there's infinite ways to parameterize things, but we're going to choose things that are most convenient for us and have the best range of t. So I'm just going to write the answer, and we'll reverse engineer it, look backwards. So here's the answer. Gamma of t equals 1 plus I plus 2 plus I times t, where t is in the interval 0 to 1. So although this might seem a little bit random, where did I get this from? I'm going to show you exactly where I got it. First, let's see that it works. So if I plug in 0 into our parameterization, then I get 1 plus I, which is indeed the starting point. If I plug 1 into here, I get 3 plus 2i, which is indeed the ending point. If I plug something like 1/2 into here, I get 2 plus 1.5i. And is that right in the middle of our path? It turns out that that is the point right in the middle of our path. So this seems to be correct, and indeed it is. So how did I do this? Well, you might notice that this 1 plus I is the starting point. So this is always the A. And now this 2 plus I is the difference between the ending point and the starting point. So that's how I did that. I did 3 plus 2i minus 1 plus I. So I got 2 plus I. And the reason I want the difference here is because when I plug in t equals 1, I want them to be added together and get the final point. And I wanted my range from 0 to 1 just to have a nice range to work with. But here's just as worthy and another parameterization. Gamma of t equals 1 plus I plus 2 plus I times 2t, for example. But now, notice that my range of t's cannot be the same. I have to take it from 0 to 1/2. Because now when I plug in 0, it's still 1 plus I. When I plug in 1/2 here, then this 2t becomes a 1, and I get 3 plus 2i. So just to make my point clear, another parameterization would be gamma of t equals 1 plus I plus 2 plus I times half t. But now you can think of it, what my range of t's has to be is 0 to 2, because now I need to plug in 2 into here to get 1/2 times 2 is 1 and get back to my b. So you can see, in my opinion, usually you want to do the range 0 to 1 or something like that, and you want to choose this parameterization so you can have a single t and not get mixed up. So that's parameterizing a line. So let's look at something a little bit more complicated, like a circle. So it turns out that there's a set definition, set parameterization for a circle as well. So here it is, gamma of t. And this circle, I have kind of covered this with my drawing, but this is 2, goes up to 2i, goes up minus 2 and goes to minus 2i. So it's a circle of radius 2 centered at the origin on the complex plane. So this circle is going to be parameterized by 2 times e to the I theta, t. 2e to the I t, where t is from 0 to 2 pi. Might seem kind of random again, but let's just give it a go, make sure it works. So when I plug in 0 into here, 2e e to the I 0 is 1, so that's just 2. So indeed, I start here. Now if I plug in pi over 2 into here, I get 2e to the I pi over 2. And from our exponential video, we can work this out. It's cosine pi over 2 plus I sine pi over 2, so that's going to be just I. So this is going to be 2i. So I'm up here now when t equals pi over 2. T equals 0 here. When I plug in t equals pi into here, I get e to the I pi, which is minus 1, times 2 is minus 2. So now I'm here, so t equals pi. Now if I plug in 3 pi over 2, I'll get right here, 3 pi over 2. And now if I plug in 2 pi, I'm going to come right back here. So we see that we follow, and I've drawn two sets of arrows here. I've drawn these red arrows and the orange arrows. So the green arrows are going in the same direction as the red ones. So it's going counterclockwise. Okay, so the reason I drew the orange arrows is you might be asking the question, hey, what if I want my circle to go in the other direction? How do I do that? So it turns out there's a nice trick to do that. How you would do it is, here's your new parameterization with orange, equals same radius. So whatever number you put here will be the radius of your circle, which you see from the calculations why that's true. So reverse, and if you want to reverse a gamma, often you put a minus sign here. So minus gamma means the same gamma taken in the opposite direction. Okay, so minus sign means take your curve in the opposite direction. So minus gamma equals 2 times e to the I 2 pi minus t. So why does this work? Because, and again, t goes from 0 to 2 pi. So now if I plug in 0 in here, I get 2 e to the I pi. So I'm starting here. Now if I plug in pi over 2 into here, I get e I to the 3 pi over 2. So now I'm coming down this way. And now if I plug in pi into here, I get this point here. So essentially it's being traversed in the reverse direction. And how did I know to put 2 pi minus t in here? Well, it turns out that the formula, if you want to reverse something, negative gamma equals gamma of a plus b minus t. So in this case, my a was 0, my b was 2 pi, and I had t, so it was 2 pi minus t. That's why I put that in here. So that's how you get your minus gamma. And the last thing I wanted to talk about was orientation, and I've kind of ran out of room here, but I can just give it verbally. So orientation, and this has to be of a simple closed curve. Okay, so it only makes sense to talk about orientation of a simple closed curve. It's the direction of travel such that when you go around the curve, the interior always stays on your left. So let me let's try to do it right here in our limited space. So let's draw a curve here. Remember, it has to be simple and closed, so it cannot intersect itself, and the ending point, starting point should be the same. Here's a simple closed curve. The positive orientation is the orientation, the direction of travel, so that the interior always stays on your left. So here's the interior, and if we go this way, the orange arrows, is it always staying on our left? So we're going this way. So pretend you're a guy right here, sticking your left hand out. Yeah, it's inside. You go around this way. Now you kind of have to reverse your way of thinking, but if you're facing this way, your left hand will be facing this way. So then that's the positive orientation, and I've written the word positive here because the video got cut off. But indeed, this is the positive orientation. Your left hand will always be facing towards the inside. Now I've drawn arrows here for the negative orientation, which you might just think is the opposite, and that's true. So the negative orientation will be the orientation where your left hand is always facing the outside of the curve, so not the interior. So if we go this way, then your left hand is always facing that way.